We concluded the first part by remarking an important caveat of the control theory, the control active system using thrusters. That in real cases, you need to know the time tau at which the thruster is firing. So you know that the thrusting is not impulsive, but you have a finite time tau that is going to affect the final time at which you have the at which you have your you are reaching your goal, so your final angle. So what we have seen is that if you assume to have impulsive maneuvers, the final time is given by this term. The discrete time at which the maneuver is firing, so the thruster is firing, is tau, and it is going to affect directly the final time TF. So you're going to reach this final time with a delay. So larger is the time of the firing of the thruster, so the time that the thrusters need to reach a certain angular velocity, to reach a certain torque, and larger will be the time to reach that angle. So in real cases, if you want to plot the angle, for example, this is the yaw angle in terms of time, what you see is that this is an example by assuming the moment of inertia along the yaw axis is equal to 150 kilogram per square meters. The T final, it is 100 seconds, and so we fixed the time at which we want to reach a specific angle 1 or 1.1 radians, and we to reach that T final, we need to know what is the impulsive, so what is the torque that the maneuver has to apply, and especially tau, that is a time given by the design of the thruster. So what it means here is that you have a specific thruster that give you a maximum torque. So for example, M0 equal to 2.1 Newton per meter. You know also tau, so you know that your thruster can fire, can reach this maximum torque after 20 seconds. With these two information, you are able to determine the final time that is required to determine a certain angle C final. So basically, this is the angle that we want to reach. By using the expression of C final, we have seen, and we know also the moment of inertia of the spacecraft, we are able to determine the T final, that in this case it is 100 seconds. It's not 100 seconds, but is basically, so these 100 seconds you can see here already account for tau. So T final indeed depends on the maximum torque that the thruster can apply with the time tau. This is the final angle that we want to reach. And so this is an example that to do that, you need to spend 100 seconds. And so what how these thrusters are going to reach this goal is by firing the thruster for the first 20 seconds. So here you see the parabolic term that we have seen for the angle time variation. For the next 60 seconds, you have a linear term of the a linear variation of the angle, and after that you will have a parabolic, so a quadratic term for the final 100 seconds, at which the thruster is firing in the opposite direction to stabilize the spacecraft at that angle psi final. Okay, so this explains how the thruster works. So let us now focus on the advantages and disadvantages of this control actuator. So the first advantage you can see, and you can compare that after at the end of the course, of this part of the course tomorrow, is that the thrusters can provide a faster response, so the lower time to reach a specific angle. So you can use indeed the maximum torque given by the thruster in order to reach that angle in a shorter time compared to reaction wheels, for example. The problem is that during these tau seconds here, so tau 20 seconds and the other 20 seconds, the structure of the spacecraft will be significantly affected by strong vibrations induced by the firing of the thrusters. So the main disadvantage is that during that period, the spacecraft will be perturbed and the structure will be indeed affected by those firings. So we need to introduce, and so for example, if your goal is to keep the spacecraft neither pointing because you need to have cameras pointing towards the Earth, or you need to have an antenna that establish communication to Earth, during those periods, indeed, that can be, those goals can be significantly affected, and you are not able to conduct your operation safely. The other problem is that if you look at the scheme of thrusters, so for example, this is a possible configuration for thrusters here, and this is the U-axis that is perpendicular to the spacecraft. If these thrusters are not perfectly aligned, you are not only going to have a torque that gives you the possibility to reach a specific altitude, but if there is a misalignment, you're going to also have, for example, an undecided thrust, an undecided delta V. This is another main disadvantage. And usually it occurs that the spacecraft thrusters, because of vibration or thermal deformation, tends to have small misalignments that lead to delta V during maneuvers. So we need to introduce another control system that overcome all these weaknesses of thrusters. And the main control device that is used for interplanetary spacecraft, but also for Earth satellites and other applications in space, are based on momentum exchange devices. So we have seen magnetotorques that are, however, limited by the fact that can work only on Earth, on planets with a magnetic field. But I mean, those are very few, since you know that Mercury has a magnetic field, but is very low, and you have other bodies in which the magnetic field cannot be used, like Jupiter or others. So basically, the magnetotorques are only used at Earth, and on top of that, you know that you are not able to provide a 3D stabilization, a 3D control with magnetotorque rows, because you are not able to control the direction along the magnetic field. Thrusters, we have seen that today, are indeed limited by the fact that provide the structural instabilities, but also the undecided delta V's. And during the firing, so the time tau, the operation of some instruments are significantly affected. There are also possible solar radiation pressure sails. However, those devices provide very small torques. So in order to reach an altitude with that device, you will need very long scales times. So the main application is indeed based on momentum exchange devices. The momentum exchange devices are based on the fact that now the angular momentum of the system, the total H that we've seen in the Euler angles, in the Euler equations, is not only HS, as for the thrusters. So basically, you when you use thrusters, you are inducing torques directly on the spacecraft, and so you are changing directly the angular momentum of the entire system. The momentum exchange device, and in particular the reaction wheels, tends to change the angular velocity of the satellites, and so you have to take into account the angular momentum of the satellites and the wheel for the entire system. So what it means here is that those devices are called a momentum exchange, because the reaction wheel is not going to provide a torque directly on the spacecraft in order to change the angular momentum of the spacecraft, but is going to apply a torque by transferring part of this angular momentum to the angular momentum of the spacecraft. So it means that the angular momentum of the system will be conserved. So H dot will be equal, big H dot will be equal to 0. So we are going to change the angular momentum of the system by changing the angular momentum of the wheel. So for example, the main concept of reaction wheels is that you have a wheel that is still in your spacecraft. You start to rotate that wheel. So you have a wheel that is still. If you start to rotate the wheel with a certain omega wheel, the torque that you are applying to the wheel in order to change the angular momentum of the wheel will be transferred to the angular momentum of the satellite. So in order to increase the velocity of the wheel, you're going to provide an opposite torque on the spacecraft. So what it means is that changing the angular velocity, the angular momentum of the wheel, you're going to change the angular momentum of the spacecraft. So those are indeed called reaction wheels, because the reaction of that torque on the spacecraft is going to provide a torque that controls, so that that is going to be opposite to the disturbance itself. So the overall inertial, so as we said, the main difference between the first devices is that they are going to change H dot, so H S dot, by providing a torque on a spacecraft. This one is going to transfer the angular momentum of the wheel to the system, to the satellite, sorry. So the angular momentum of the system will be conserved. There are other devices. So the devices we are going to only show are indeed the reaction wheels. But in literature and in space systems, you can find, for example, momentum wheels and control momentum gyros. So for example, the momentum wheels have a different are based on a different principle. So the wheel is going to spin and to provide the gyroscopic stability to the system. So you know that if you have a wheel, for example, that is rotating, fast rotating, in order to change its orientation, you need to apply a torque that is going to lead to the precession of the axis of the wheel. So basically, the angular velocity of the wheel is going to provide a larger gyroscopic stability to the wheel. So it's basically more a passive device, because basically it's going to use the stability of the wheel itself. For the reaction wheels, we are going to change the velocity of the wheels in order to transfer angular momentum from the wheel to the satellite. The other things that you can use are control momentum. So the momentum wheels, for example, were used on the International Space Station, and or for example also on the Space Shuttle, in order to indeed maintain a certain stability. Control moment gyros are, for example, used on CubeSat, and we are not going to see that in details, but basically are based on the fact that you can vary the spin of the wheel, and you can also change the orientation of the wheel in order to provide different rigidity of the system in different direction. So as I said, we are not going to treat the control moment gyros. So if, it will not be clear from this lecture, but if you are interested, you can see in literature the application, or we can discuss tomorrow briefly. But the main goal that we need to address today and tomorrow is indeed the reaction wheels, because represent the main device used in space to control the attitude of the spacecraft. As I said, because the main concept is indeed to provide directly a transfer between a transfer of the angular momentum from the wheel to the system. Those two tends to use the gyroscopic stability of a wheel that is rotating. Okay. Before going to the detail of the wheel that will be seen tomorrow, we need to introduce a control scheme that is much more complicated compared to the bang-bang, for example, but is something that probably you already have seen in other courses based on the stability of system in general. And so what we are going to use is indeed the difference between the measured angle from the sensors and our goal, that is our theta desired, to develop two control schemes that are going to provide continuous, so torques that are going to vary continuously over time in order to maintain a certain desired attitude. So even if you have a disturbance or if your goal is to point from one angle to another angle. So our goal here is to use this information, so theta desired minus, theta measured minus theta desired, that is our error, to develop a control scheme that uses this information, that it will be indeed used in a feed-forward controller, to generate a certain torque, on the system. So basically, UT will be directly related to the error, so the difference between the desired attitude and the measured attitude. So as I said, we are introducing them now because the reaction wheels has the possibility to change continuously the velocity of the wheel, and so change continuously the speed, the torque that you are going to apply to the system. You are not able to use thrusters in this schema because, as I said, the thrusters works with the maximum torque for a specific time, tau. That's the reason why the bang-bang approach is the one that you have to use for thrusters. Now we are going to introduce a control device that enables this continuous variation of the torque of the system. So the control scheme that you see here is called a closed loop scheme. The closed loop scheme means that you are feeding back the information that you are having, that you are collecting from your sensors. So as I said, if you want to summarize the problem, here you have the observation. You use, for example, your quest algorithm, and you determine the quaternion. You can transform the quaternion by using, if we're assuming small angle approximation, theta. So these will transform in theta, and this theta will be indeed our theta measured. The reason why you need to do that is because usually your desired attitude is in terms of angles. We are going to deal with angles because, for example, our desired goal is to have that the desired pitch or yaw angle will be equal to 0, for example. Okay, so the control scheme is pretty straightforward. So you have your desired state, that is your theta desired, your orientation in the roll, pitch, and yaw axis. And you do the difference between your desired state to the measured. Go to the regulator. So the regulator is going to give you indeed, so it is a part of the controller. So basically give you the difference between the, so what you need to know for the control torque. So you will need to have this information to develop these two blocks that will be clear in a moment. So these information, so this error between the measured and desired state, will give us the control that we need to apply to the actuators. So the actuators will receive the input from our controller. So this is the scheme of a controller. That basically it is important because it is what we need to apply to the, for example, to the reaction wheel in order to keep a certain attitude. So the controller is going to provide our TC, so the control torque, that we need to apply from the actuator. So the actuator is going to apply this TC, and the dynamical equation, so the Euler equations, will account for the control torque that we received from the controller to change our state. And so the loop is going to be closed with additional measurements from our sensors. They're going to go back, they give us the estimated measurement state, and so the loop will continue until we reach our desired state. So the main reason why here we're able to use this kind of schema is also because the formulation that we are going to use is based on a linear time invariant system. So we were able to use to determine the dynamical equation of a system that provide a linear time invariant system. So what I mean with the linear time invariant system? So the linear time invariant system means that usually this system have an input x dt and will provide an y dt. Okay. So the linearity, so the linear property of this system means that if you have, so the linearity of this system means that if you have, for example, one input signal xit, that in our case, in the previous case, it is u. So our input is the control torque that we're applying to the system. You're going to provide a certain y dt, y1 t. And if you have x2 dt, you will have add y2. So the linearity means that, so the linearity property means that if you have the combination, the linear combination with the scalars a1, a2 of the input signal x1 and x2, so this is x2. So this is the input. The output will be the combination, the linear combination of a1 y1 plus a2 y2. You can extend these properties by using a sum. So for example, for k of ak of x, k function of the time, so this input can be indeed equal to the sum of k, ak, and you can also extend with integrals. So this is an important property, but the other important property, so this is the linearity. The time invariance of the system that is also verified for this system, for the attitude control system that we are going to introduce, is given by the fact that if you have the same response, so if you have a certain signal shifted by a certain time tau, the response will always be y shifted by the same amount of time. This is the time invariance. Why it is important? So we are not going to see all the details of that expression, but it is important because basically these time invariants in the time domain are usually tied with a certain function h, and the y dt, so the response to this impulsive response h dt is equal to the convolution of the two. So it is ht time the convolution of x dt. So it means for those of you are not familiar with convolution, that is the integral from minus infinite and infinite of the h tau x t prime minus tau of the tau. So for you probably, so this is in the time domain. So for those of you who are not familiar with that, I mean, it is not really important, but it is only important to know which is the definition of a linear time invariant. So because of this these properties, you should be able to find an impulsive response of the system that goes from the input to the output. As I said, the input is xdt and the output is ydt. So in terms of, so this is in the time domain. The reason why this is important is because if you want to pass from the time domain to the frequency domain, you do the Laplace. So if you want to go from the Laplace domain to the frequency domain, basically, if you do the Laplace transform, there will be x s, the transfer function h s, y s. It means that the convolution in time domain will be a product, a multiplication in the Laplace domain. So you can find a transfer function that give you the certain response of the system from a certain input x. Okay. So this is the term, what it means linear time invariant. And if you compare with the orbit determination, these properties are not satisfied in that case. So this important consequence is indeed that we are able to use the properties of a linear time invariant system to develop an important control system. So the first control system that we are going to see, and we're going to see better tomorrow, is indeed the PD controller, so the proportional derivative controller. So let's assume to have our pitch dynamics, okay, in the solar system. So we are in cruise, we don't have any significant disturbance right now. So that will be equal to 0. But let's assume that you have a spacecraft with a solar panel, asymmetric. So basically you are going to have a disturbance given by the solar pressure, a constant disturbance. So for example, this is your solar panel, this is your spacecraft. And let's assume it is your pitch angle, so your y. And so basically you're going to have a disturbance in that direction, okay? You want to develop a control scheme, so a control torque that is going to be opposite, so it's going to counter-react to the disturbance. So linear time invariant system enables to determine a control scheme that depends on the error. So our goal now here is to have that theta desired is equal to 0. So basically that although we have a disturbance, the spacecraft has to be still. It means that you can develop a control scheme that is based on the error. So for example, it will be minus k p times theta desired, so theta measured minus theta desired. And in this case, it will not be theta measured, as I said, but it will be the theta that you are going to integrate over time, okay? Minus k desired, kd times the theta that you're going to integrate. And so it is going to vary because of the disturbance, minus theta desired. Since our theta desired is equal to 0, so we want, sorry, not only theta desired equal to 0, but we want also that theta desired dot will be equal to 0 as well. So we want to have this angle, but also that it will be still. If you apply this torque that here is called MC, but it should be TCY, well, you are going to determine this dynamical equation. So the moment of inertia, so for brevity, I will only use y. dot plus KD. So since I have said that the theta desired is equal to 0, that will be KP, KD, KP, theta equal to the disturbance. So the first goal that we need to do is we applied this linear controller because we have a linear time invariant system. We have to verify if this controller is going to, first of all, provide a stable system. And secondly, is going to provide us so our desired angle. Okay? So the stability of this system is usually determined in two ways. We're going to see two approaches. The first approach is based on the Root-Hurwitz criterion. So the Root-Hurwitz criterion, or Root-Hurwitz criterion, is a method for determining if a linear stable is stable or not. This criterion only give you necessary condition for the stability. Okay, so those the following conditions has to be verified, but will not be sufficient to provide stability. So if you write the characteristic equation, so that will be indeed this one. So basically you write lambda squared y plus kd lambda plus kp equal to 0, because the stability is always investigated using the associated, the homogeneous associated to the matrix. So we have to see if this will be indeed stable or not. So the Root-Hurwitz criterion give you the conditions to this characteristic equation that for our case is pretty simple. So all polynomial coefficients must have the same sign, and all polynomial coefficients must be not 0. So the A coefficients here, that will be our I, KD, and KP, has to be with the same sign, so positive, because we know that the moment of inertia is positive, and has to be non-zero. So we are not able to provide any KP and any KD equal to 0. To develop, to provide, if these two conditions are satisfied, we can provide the conditions for the criterion of the Root-Hurwitz. So the table of this criterion seems to be difficult, but actually it's pretty straightforward because we only have a second order equation. So basically the first row is given by the coefficients an minus 2, an minus 4, an minus 6. The second one, an minus 1, an minus 3. So basically, in our case, it will be a2, a0, a0, and there will be a1, okay, as it is written here. So it means that all the other coefficients for our will be 0. So the other row that we have to consider is only this row here, and will be indeed given by the determinant of this submatrix divided by an minus 1, so this term here. And so if you study in detail this criterion, you need to find that all the terms in the first column have to be positive in order to have a stable system. So let's do this criterion to this system. As I said, it is more complicated because it's general for every single system. But you can see that this criterion provides so the necessary condition that all roots have negative real parts. so that the system, so the necessary condition to have asymptotic stability, it is different to what we have seen for gravity gradient, that we have seen only stability, but not asymptotic stability. So the necessary condition that we need to have asymptotic stability is that all the elements in the first column has to be positive. So it means that if we use the characteristic equation that we have here, the first row is pretty simple because it, as I said, is A2 and A0. So it will be IY and KP. The second will be KT and 0. If you do the determinant of this one, it will be indeed equal to minus KD, KP divided by minus KD. So the third row is equal to KP. If you want to compute this table in detail, you should use this scheme here. So the first row, the first column is what is important. All those elements should be positive. The moment of inertia is positive for definition, but we found two important conditions on KT and KP. So we have seen that KP and KD, in order to provide a stable system to counter-react to the constant term, has to be positive. So we conclude with that, and tomorrow, so the first thing that we have seen that if we want to control a system, a linear this system with using the PD control scheme, we need to apply KP and KD positive values, with positive value, to have the necessary conditions for the Rautorwitz criterion of asymptotically stability. Tomorrow, we are going to see basically that this system can also be seen by going to have a quick look on the stability of a spring mass of a spring damping with a spring mass problem with a damping. And so we are going to see that the same conclusion that you do for that case are similar for the system with a PD controller. So basically, the main conclusion is that if you have a constant disturbance, you are not going to have that your theta desired are going to converge to what you want. So your final theta will not going to converge to your theta desired. But that will be clear tomorrow. And that's the reason why we're going to introduce the PID controller and conclude this part of the course by providing information on the reaction wheels. So how the reaction wheel works by using PID controller. Okay, so let's stop here.